So it's a pleasure and privilege to have Professor Sriram Shastry giving us a colloquium all the way from Santa Cruz. I hope one day he'll visit in person after COVID and all blows over. So I promised him I'll make this intro as simple as possible, but not simpler. So Sriram did his PhD at TIFR Bombay, and he has worked at several places subsequently. Soon after his PhD, he went to University of Hyderabad and then to Imperial College London, to Utah, and then he spent many years in TIFR again, and then in Bell Labs, and then he spent about 9 years in IISc Bangalore, which is where I was his PhD student. And subsequently, he moved to Santa Cruz, where he is a distinguished professor of physics now. And his research interests, as many of you know, encompass a huge variety of fields, from exactly solvable integrable systems to thermoelectric phenomena, to spin ice and frustrated magnetism, to what he'll be talking about today, which is the puzzling cuprates, which have been puzzling us since the 1980s when they were discovered. And he has his theory of extremely correlated Fermi liquids, which he will tell us a little bit about today. So with no further ado, Sriram. Thank you.
Thank you. So thank you very much, Rahul. And
let me add, by the way, sorry, that Sriram said he's happy to be interrupted during the talk. So please raise your hand. I will also be keeping an eye, or type a question in a chat box, and we can take the question at that time, and also after the talk. Thank you.
Yeah, so I'm delighted to be here and to be with friends and with former teachers, and also some of my classmates are here from TIFR. They have joined here today, like Dilip Kale is here. Thank you, all of you, for coming. And again, this is supposed to be colloquium, so I have tried to make it very qualitative. It cannot be entirely qualitative because ultimately there is a lot of, heavy machinery which grinds underneath the hood, so to speak. But I want to convey the basic ideas behind what I'm calculating. And I would like the audience to stop me. If you don't understand anything, raise your hand, either like this or digitally. There's a way of raising your hand through the participants. In the chat box, you will find, or maybe, how do you raise the hand digitally, Rahul?
The reactions.
Yeah. Thank you. So you can use reaction to stop. And if I miss your question, please ping Rahul and he can talk to me and he can stop me. So I want to talk about unraveling the puzzling cuprates. There's a lot of work which has gone on in this area by a lot of people. But my own interest in this problem has sort of kick-started about 10 years ago into a new way of doing things, which is what I'm going to tell you about, a new way of calculating things. And a lot of the reprints relating to this approach there's a collection of reprints which you can find on my website here. So I want to start with a little bit of historical timeline for people who are not condensed matter people. I'm sure there are some people in the audience who are not even condensed matter people. So you would like to know, why is this cuprate stuff so interesting? What is keeping it, interesting to so many people, so many years? So I want to give you a very quick and a very rough overview of these things. So, the game began, so to speak, in the year 1987. When people discovered material called LSCO. It is lanthanum strontium copper oxide. It's called one layer, which simply means that in the unit cell, there is one layer of copper oxygen, as opposed to other systems which have 2 layers and 3 layers within a unit cell. And of course, the number of unit cells is very large. It's like the number of, it's like the Avogadro number. But one layer is somewhat simpler. And this is the first material which was first found. And it's so-called hole-doped, and I will explain what hole-doping means. It's also very close to a Mott insulator, Mott-Hubbard insulator. And I'm going to explain to you what the Mott-Hubbard insulator means. So this initial work, discovery, was very rapidly, succeeded by events which, exploded. For example, in the year 1987, there was a thing which is often called the Woodstock of physics, because one of the APS March meetings suddenly one of the sessions became so packed that people were flowing into the corridor, and people like Anderson were not able to get into the room, and so it became really almost hysteria on this topic. And there's a little review of that recently. But in this period, a lot of things happened. The materials, people found 2-layer materials, the 3-layer materials, and so on. And the transition temperature shot up to about 100 degrees Kelvin. And the number of experimental papers, this is a very rough estimate. It is about 500 papers in that 2-year time window. And the theoreticians also went ballistic. People started doing all kinds of things. Everything you can imagine doing was done. There was analytical work, numerical work, phenomenological papers. And I would say in that year, those 2 years, maybe 100 papers. This might be a serious underestimate, actually, but I leave that to you to fill in the details or to guess or to correct me. And the next decade, there were many, many more cuprates discovered. TC went up to 130 or 150 is about the record even today. And I think there's an error bar in the exponent here. I got 10 to the 3 or 4. It might even be 5. I really don't know. It's just enormous number of papers, experimental papers have been written. And theoretically, too, thousands of papers have been written on this. And more recently, further, more complicated systems, no longer having copper, but iron arsenide and so on, they have been discovered. And so this explosive activity in this whole area. So why is it so exciting? Well, the answer is twofold. One is, higher the transition temperature is technologically very promising, and that you hardly need to say that. The applications are many. You can think of lossless power transmission, and you can think of magnetic levitation, high-speed train transport. China already has trains which are running on magnetic levitation principle. But I'm a theoretician, and I want to talk about today about the theoretical aspects of this problem. Why is it interesting to theorists? So a theorist like me is interested by the fact that you have superconductivity without phonons. It looks like this is not a non-phononic mechanism. And it's a new frontier going far beyond the good old Bardeen-Cooper-Schiffer theory, BCS theory, which was, mid-1950s it was discovered. The theory was discovered, and it kind of ruled the arena of superconductivity for nearly 30 years. And we have to go beyond that. So there are no phonons anymore. Something else is binding superconductivity. And then there is this word called strong correlations, which some people know very well, but there'll be others in the audience who won't know it. And I will explain what I mean by strong correlations. And I will also say one of the things which is theoretically exciting is the temperature dependence, extraordinary temperature dependence in transport. Now, all these need some explanation because none of these is universally understood. Condensed matter, people know it, but not everybody is a condensed matter physicist. In fact, in this audience, there are other people. So strong correlation is basically a code name. What it stands for is beyond Feynman-Dyson perturbation theory. So, we have to understand the physics of many degrees of freedom which are interacting with each other in a highly quantum state in a regime where Feynman-Dyson theory simply cannot work. Now, so quantum theory in the non-perturbative regime is, of course, a common denominator to many other challenging problems in physics. I mean, many high-energy people are interested in this, nuclear physics. Everybody's, stumped by non-perturbative effects. So it's challenging and unprecedented. And just some background to perturbative versus non-perturbative. If you glance through any book in quantum mechanics, we see that the books present results from, textbooks give you very simple closed form expressions which come from either linear or very special problems. I mean, just as an example, harmonic oscillator, hydrogen atom. I mean, there is no textbook which tells you the solution of the anharmonic oscillator, for instance. The anharmonic oscillator doesn't have a closed form solution. It's a slightly more difficult problem. It can be solved numerically, but there's no closed form expression for those things. So there is a difficulty in solving nonlinear problems already at the level of 1 degree of freedom. Books also concentrate on perturbative solution. Perturbation theory is, of course, a large part of what we learn in quantum mechanics courses. And the same thing is true in textbooks on many body physics or field theory. But the one big exception in this sort of bleak horizon is one dimension. In one dimension, there are exact solutions of really non-trivial problems. For example, even the Hubbard model that I'm going to talk about today is solvable in one dimension by a very special technique, which works for some magical reason, something called quantum integrability. But that is so confined to one dimension that, real life, most of the systems we talk about are in 2 and 3 dimensions. So that doesn't really help us much. So the Mott-Hubbard system, which I'm going to talk about today, is intrinsically one of the most difficult theoretical problems faced in condensed matter physics, and maybe in any kind of field theory for that matter. So here, the Hamiltonian has a coupling constant, which is very large. And this is combined with a large number of degrees of freedom. And there's a third piece of the puzzle, which I will explain in a minute. The density comes into play. And normally you think of quantum mechanics, there are these kinematical parameters or coupling constants. We don't think of density itself as a parameter per se. But the Mott-Hubbard systems require us to view the density also as an important parameter. So this is a challenging problem. It's a frontier problem because all known techniques have failed to solve this problem. Everything we know in numerical, analytical, everything is kind of stuck here. We can't really do this. So I want to take a minute on giving you a cartoon of what the Mott-Hubbard problem is. And this actually, I'm very happy to talk about this because scattering theory is something I learned from Rajaji, so 45 years ago. So I'm a bit embarrassed to talk about this, but it's interesting. So Mott-Hubbard problem has 2 features which come together. One is understandable without much effort, namely large coupling constant. The other thing is commensurate density. I'll have to explain that to you. So let's start with something as simple as 2 electrons interacting in a vacuum. So we have kinetic energy, some potential energy, and there's a large coupling constant. But large coupling constants in one electron problems don't bother us much because we have the so-called partial wave analysis. So basically, interaction can be very large, but basically the deltas are the only things which matter, and deltas are bounded between 0 and pi, or maybe between minus pi and plus pi, depending on the convention. And maybe there are some bound states which can appear, but for repulsion, there are no bound states. So basically, the coupling constant can be large, and if you try to do bond series, you'll die very soon because bond series doesn't converge. And then you quickly convert and say, look, I'm going to do partial wave analysis. I'm going to look at the phase shifts. And, think of the scattering length, for example, which is well behaved even when G goes to infinity. And in fact, I would recommend thinking of the scattering length as the radius of a hard sphere. So think about a hard sphere scattering. So AS is roughly like the radius of the hard sphere, okay? So now the question is, what about multi-particle system? What happens when you have many particles? So this is now a challenging problem. And here there is a beautiful idea, qualitative idea put forward by Fermi. And Fermi said, don't deal with the bare potential, deal with the pseudo potential. And you can always think of a pseudo potential which reproduces all the scattering which is happening to low orders by working with the pseudo potential. So you get exactly the same answers that you get by summing. Oh yes, Dr. Govindarajan.
Sorry, can I ask a simple question? See, even though the perturbation series can be divergent in the when you have to go to non-perturbative things, unless it is essential singularity, you don't have a serious problem. You can do several approximations like Pade approximation. You can make sense out of infinite divergent series by doing some tricks with that. Is that not possible here?
No, you're absolutely correct. That Pade kind of analysis works for a single degree of freedom. So, but what we are dealing with is a many particle system. So you have a wave function with many coordinates. So actually the difficulty comes from the many particle aspect of it. And even with many particle aspect, Fermi's idea actually solves most problems, like nuclear matter, nuclear physics, we're dealing with nuclear matter where the interactions are so strong. And yet we get very qualitatively and even quantitatively reliable answers because we are doing some version of Fermi's idea. So no, you're perfectly right. If you have essentials, what you said is correct. You can do Pade approximation. There are good techniques available for dealing with nonlinearity. But I think when you have large number of degrees of freedom in a field theory, it becomes very difficult. Is that okay? Are you good with that?
Okay.
Yeah, okay. So Fermi's idea was basically take a pseudo potential which is parameterized by just the scattering length, AS. So everything else here is fixed by, delta function is a delta function, this is a mass. So the only parameter you take from to define the pseudo potential is the scattering length. And Fermi's, beautiful intuition was that low orders with the pseudo potential will give the same answer as to all orders with the strong potential. And, there is a wonderful series of papers by T.D. Lee and C.N. Yang in the mid-50s. And these are really forgotten papers, but I was looking through them recently. Absolutely beautiful papers. They implemented Fermi's idea. And they actually found that you can get exact results for the energy of the system, for a many particle system, provided the density is low. So this is where some of the interesting things begin to happen. Kf is a Fermi wave vector, which depends on the density, of course. So provided Kf times the scattering length is much less than 1, you can get formally exact results in the low density limit. Now, the difficulty is also immediately visible to us when the density increases, okay? So, and if you have a box with finite volume, and you start putting more and more of these hard sphere balls, at some point you reach a jammed situation where the hard spheres are touching each other, right? So that's where the Fermi-Lee-Yang method fails. And so, for example, these hard spheres are touching each other, and I've given these hard spheres an arrow, which is like a spin degree of freedom. And here, the AS is like the interparticle spacing. So this condition is badly violated. So once these particles begin to jam each other, this is a crude cartoon of the Mott-Hubbard insulator. Because, here particles cannot move. To move, you have to push something out of the way, but there's no room. So you actually get an insulating state where charges are trapped. Put an excess charge, it cannot travel. So from a metal, you get an insulator because you've reached this hard packed limit. And of course, this hard packing is happening quantum mechanically. This is not a classical fluid anymore. This is a quantum fluid. And in fact, helium-3, the helium-3 is a superfluid, which is often described by models which are exactly like this. So here, the spin degrees of freedom remain, although the charge or the positional degrees of freedom are locked up because of the, the jamming. So the insulators are fully packed metals. When you remove a few atoms, so for example, if I go in here and take out a few atoms, then I've created some vacancies. Now these vacancies can certainly move around. So you restore conduction by removing some particles from this limit where you're jam-packed. And the jam-packing is often called n equal to 1. N is the number of atoms per unit cell. So n equal to 1 means you're jam-packed. And if you start creating some vacancies, if delta is some fraction of vacancies, then the metal goes to an insulator. So this is a cartoon of a Mott insulator. This really happens for inert gases, for helium, for argon, certainly reach this kind of a situation. But Mott-Hubbard technically is for electron. Actually, translate this whole story to electrons now. Electrons are jam-packed. And of course, electron physical size is so small that you can't really speak about hardcore interaction with them. But effectively, in a unit cell, you can have only one electron and no more. And that's a commensurate. A commensurate means, the density is linked to some sort of a geometrical number. So, okay. So the Mott-Hubbard problem that I'm going to discuss is a generalization of this to electrons. Okay. So let me talk about, okay, so here I said this resistivity. I use the word extraordinary temperature dependence in transport. I also said strong correlation. I explained what strong correlations mean. It's like being in the Mott-Hubbard limit. And temperature dependence of the transport is exceptional. Let me explain what that is. And before I go there, let me just make a little caveat here. In this Mott-Hubbard description, you saw there were two parameters. One was the coupling constant, G, which was traded for the scattering length. But the other parameter which entered was the density. When n equal to 1, you are stuck into insulator. When n is less than 1, you can get escaped insulator. You can escape the jail and you can begin to conduct. So density, in a very strange and interesting way, becomes a dynamical parameter that you have to worry about. So this is something which comes back in the Mott-Hubbard problem. It's something unexpected. I mean, people who don't do condensed matter, who don't do dense matter, they would never think of density as a parameter, But it is a parameter in this sense that you can jam particles and then, create vacancies and stuff like that. So now I want to talk a little bit about the importance of resistivity. I'm going to talk a lot about resistivity, why resistivity is so important. Well, in our courses in condensed matter physics, we never emphasize this enough. But if you go to some, lab with top-class experimental physicists working, they will tell you that if you give them the plot of the resistivity as a function of temperature, they can tell you a lot of things about the material already. And the reason is that the resistivity, of course, a dissipative object, but it tells you what are the low energy degrees of excitations. What kind of excitations exist at low energies. So just as an example here, think of insulators and good metals, and the cuprates is an example of a good metal, it turns out. But Roger, the resistivity in an insulator goes like exponentially. As T goes to 0, resistivity goes to infinity. insulator. And delta tells me there's a gap of some sort. This is energy gap. In a good metal, we see resistivity, which has several components. C naught comes from impurities. Impurities give you temperature independent resistivity, which adds to something which is usually T squared. And there are also some other things like T to the 5/2, which is a higher order correction, but T squared is usually what you see. And this comes from electrons scattering from each other and dumping momentum into the electron bath, which finally have to, of course, get rid of the momentum by giving it away to the lattice through something called umklapp. So that's the complicated sounding thing, but physics is very simple. Really, physics is inelastic scattering of electrons from other electrons, has a phase space constriction, and the phase space limitations give you T squared. And this is valid for temperatures less than the Fermi temperature. And the Fermi temperature in a metal is typically 1,000 degrees Kelvin. It's a pretty large number, 1,000, 2,000. And the Debye temperature in a good metal is typically 500 Kelvin, which is the oscillating frequencies of the phonons. And in fact, when you exceed 500 Kelvin, you do get temperature which is linear with T, but only when T is bigger than 500 Kelvin or so. Cuprates, it turns out they have impurity piece just like good metals. And instead of ever finding a T squared, you find T. And sometimes T comes with variable exponents, T to the power of 1 or 2, 1.2, whatever. So you get something which is not so universal. And the Debye temperature is more or less the same as that of a good metal. So it's a very mysterious object because it's got this T rather than a T squared. You expect a T squared, you never see T squared in the laboratory regimes of temperature. And the scales of resistivity, of course, resistivity also comes with a magnitude, which has got an important story connected with that. So in insulator, you get kilo or mega ohm centimeter. Whereas in good metals, you get micro ohm centimeters. And cuprates also give you micro to milli ohm centimeters. So these are really good conductors, but they seem to have a very, very low Fermi temperature. Fermi temperature seems to be much smaller than the Debye temperature. So understanding this is very difficult because the Fermi temperature is usually set by the electronic bands. And the electronic band width in these cuprates remains like 10,000 degrees Kelvin, very big. So why is the effective Fermi temperature shrinking? This was a puzzle. So I've given you like very long introduction to non-condensed matter people just to keep people happy. But now I'm going to switch gears to a little more specialized things. So in this talk, I'm going to talk about my work, where I have a lot of puzzles, and I'm going to think of each of the puzzles as a ball of string, which I want to untangle. I'm going to talk about three systems. I'm going to talk about these three compounds. They happen to be single layer cuprates. Single layer cuprates. And two of them are hole doped, one is electron doped. So electron doping versus hole doping is simply, you have this jam-packed state, and you start pulling out particles, you're creating holes. Whereas if you dump extra particles, I mean, it may sound like it's going to be infinite energy, but let us say you pay the energy cost somehow, and you confine the things, then you have some extra particles in addition to half filling, and they are electrons, and they wander around. They can go around and conduct charge. So one of them is electron dope, two of these are hole dope. And I choose them for a reason, which I'm going to explain to you why the theory is choosing these things. So I'm going to talk about two things in this talk. One is a phase diagram. Phase diagram is the TC here versus the filling. So this N is this Mott filling, and N equal to 1 is the insulator, which is here. So one typically sees insulating state here. This AF is an insulating state. Then you see a metallic, a superconducting state in which there are two densities which come out of nowhere. There is one delta smaller, one delta bigger, and there's a delta star at which TC is high. So this is very puzzling because in these cuprates, because TC is high. You get 50 degrees Kelvin, which is much higher than anything seen before with phonons. And it's known to be non-phononic because the order parameter symmetry can be measured, and it's no longer S wave like in phonon problems, but it turns out to be D wave. So singlet D wave pairing is the observed Cooper pair symmetry, which very good experiments which tell you unambiguously that that's the symmetry of the order parameter. So then we want to understand why is the TC like 50 Kelvin, and what is the kind of physics which determines these three densities? And this has been a big mystery. And then I'm going to talk about resistivity versus temperature on a few varieties of compounds. And this is a typical example of the data that I'm trying to understand. So your resistivity versus temperature, you see an X here is the same as delta. I'm sorry, different experimentalists use different names for the same physical object. What I call as delta has suddenly become X. And you see that as a function of X for different densities, this is one of the best studies done in literature. There's a man called Ando, who really specializes in making very beautiful, well-crafted materials. So there are these resistivity curves at different densities, and they all show sort of interesting behavior. The magnitudes are changing, and the temperature dependence remains linear over a big temperature regime. Here it goes superconducting. When it goes to zero here, this is a superconducting phase. And you see some curvature when X is small. So this data is pretty remarkable. It's got temperature dependence, which is remarkable. It also has density dependence, which is remarkable. So I want to understand all these things, You may say, why not study 2-layer and 3-layer cuprates and so on? Yeah, Ganesh, yes. Unmute yourself, please.
You were talking about Debye temperatures just a couple of slides ago. I'm just wondering, when you say a temperature is below the Debye temperature, is the Debye temperature obtained experimentally, or is it estimated using, say, reasonable parameters, say mass of the nuclei, etc.?
I think it's both. That's a good question. I think estimating the Debye temperature turns out to be relatively straightforward. The phonons are well measured, You can measure the phonons for neutron scattering and the phonon energies. And from them, you can get a good estimate of the Debye temperature. And also, heat capacity has, electronic piece and phonon piece. And you can separate. So in the beginning, when the materials were very crappy, it was, a lot of guesswork. But I think later on, much more refined data is available. So I think these numbers are, supported by both theory and experiment.
Excellent. Okay. Thank you. Thanks.
Yeah. So the question is, why not study very complicated things? And why not study iron arsenide? The answer is, I want to talk about at least the Hamiltonian, from which I start, should be simple. Not be easy to solve, but at least it should have the least complexity. A good problem is got at least a sharp and a simple statement. The problem itself may be very hard, but if I take like 5 pages to describe the problem to you, then I'm sort of killing myself at both ends. So it's a bit like solving the hydrogen atom, in the periodic table before you start talking about argon or copper. So that's roughly the spirit of why we talk about something simpler. And these have the smallest number of active degrees of freedom. And what I mean by active degrees of freedom is the Fermi surface has only one sheet on this at the chemical potential. And this is a very important statement because, this directly tells you what kind of a Hamiltonian you're allowed to write down. So I want to just remind you that photoemission, the angle resolved photoemission technique, has become very, very powerful in the last decade. And you can basically go to the chemical potential of the system and find out exactly what are the bands which are crossing it? Band, E versus K. And if you know exactly where the Fermi energy is, or the chemical potential is, then you can easily discover how many sheets there are of the Fermi surface. And there is unambiguous data available for that. So here, there's an example of a Fermi surface in lanthanum, strontium, copper, obtained from photon emission. So this gray area is the occupied states. White is the unoccupied states. And here, X is increasing this way, or delta is increasing this way. So the number of particles is increasing this way, to the right. So you see the Fermi surface area, which, by the way, is linked to the number of particles through a theorem, which is called the Luttinger-Ward theorem. The Luttinger-Ward theorem is a very, very important theorem, actually. It tells you the system is somewhere in the proximity of a Fermi liquid or a Fermi gas. So the area evolves with the density exactly as this formula says, okay? And there's only one sheet at the Fermi level. So the Fermi surface satisfies the Luttinger-Ward theorem, and we can fit the bands to a simple tight binding model with a dispersion epsilon of K, which you can figure out. So a little more detail than is perhaps absolutely necessary, but let me just say that copper-oxygen layers contain both coppers and oxygens, and each of them gives some electrons, and they go into the bath and they mix a lot and they create bands. So ultimately, per unit cell, there are 3 atoms in the bare bands. But the fact that there is only one sheet of the Fermi surface tells you that there must be some quantum chemistry jugglery which is going on to create effectively one single one-year state per unit cell. Okay, and what this means is that when you write your Hamiltonian, your electron operators basically have a spin label and a site label, but no band label. There's a single band. And the interaction can be very complicated, but the hopping is a single band. And n hat is the number of electrons at the site I, it's an operator. N is the average of that. And little n less than 1 is hole doped. N equal to 1 is half filled Mott-Hubbard insulator. And more than 1 is electron doped. So now this is set the stage for the real calculation that I'm going to talk about, okay? So I'm going to talk about something like a Hubbard model. So you have 2-dimensional electrons, which is sitting on some lattice. They hop around and they interact. And these TIJs are known from photo emission. And V can be guessed. It's one of many things, and we will talk a little more about that. I actually want to sort of make sure that I'm not leaving any of my high energy friends behind. Is Rajaji, are you okay with the introduction, or is there something I can say more? Okay, Rajaji seems happy.
Yeah, if anyone has questions, feel free to raise your hand.
Okay. Okay, so now I'm going to say that...
May I ask a quick question? Sorry, before you go ahead.
Sure.
So you set the stage as a strongly correlated system. And then, but in the previous 2 slides, you've described the electrons as forming a nice band that can be experimentally accessed in a way that conforms to a non-interacting or non-correlated system. So there must be a certain limit in which that's valid, right? Perhaps you could just clarify.
That's a very good question. So let me answer you that. See, this Hamiltonian is very complicated, okay?
Yes.
But at least one term in the Hamiltonian is simple. Right. Second term brings in all the complexity. This is a wickedly difficult problem, but all the wickedness and all the difficulty is put into this V interaction.
I see.
And if you have multi-layer systems, then even this has to be, 2-layer and 3-layer. And there are, levels of complexity which are,
I see.
They are unnecessarily complicated. So I want a problem in which at least one part of the Hamiltonian
It's simple.
is very simple. And, by the way, I should say this gives an opportunity to say that Luttinger-Watt theorem is telling me, Luttinger-Watt theorem says the Fermi surface evolves continuously with density, which tells me that the Fermi surface, the Fermi gas, has a ground state, which is certainly not the ground state of the interacting problem. But the interacting problem is not viciously orthogonal to that. I mean, it's somehow tracking it in some way. It's, adiabatically, if you wish, continuous with the Fermi gas. That's the statement of the Luttinger-Watt theorem. Okay, so I want to say a few things about the technique which I'm using here. And I want to say about what I do. And I also want to say a little bit about what I don't do. And this is very important to say because I feel that each of these no-nos that I'm writing down here has actually been used by essentially the entire community has been using most of these things. And I just want to say in a few words why I think it is so dangerous. So I want to use a single band system, and the interaction is chosen to be the TJ model, and I'll explain what that model is. It's like the Hubbard model. It's a variation of the Hubbard model. And it was actually first proposed by Phil Anderson, and our own Bhaskaran was actually very much around. Bhaskaran, Zoe, and Anderson were one of the first people to discuss this model. So there's a continuity from the free Fermi gas, which is very comfortable to have. Luttinger-Watt theorem is satisfied experimentally, and the method I use satisfies it at every step. And what I do, and this is something where I think the non-perturbative aspect comes in, I actually find non-perturbative exact functional differential equations for the Green's functions. So, Feynman-Dyson theory can also be obtained from functional differential equations. And, the Schwinger-Tomonaga methodology can be used to go either to Feynman or to Schwinger way. I use exactly the same technique to get exact functional differential equations, and they turn out to be very different from the Feynman theory, standard QED and so on. They're very different. They have extra terms, which are exactly, you can write them exactly. And then you can solve those functional differential equations iteratively. So it's like doing an iterative solution of exact equations, and it bypasses, the difficulties of perturbation theory, because I'll tell you a trick which I use. So I never work with an expansion in the interaction. So the Feynman theory, the reason it's problematic is because the expansion parameter in the Feynman theory, Feynman-Dyson theory, is the interaction parameter itself. So the interaction is very big. It's sort of meaningless to expand that unless you're very lucky to reach some infinite classes of diagrams and so on. So here, these functional equations are solved by expansion in a parameter, which has got nothing to do with the interaction. And the parameter lambda, which I'm going to talk about, lives between 0 and 1. So it's a very safe parameter to expand in. And this method uses band parameters which distinguish between electron doping and hole doping. And this calculation can be done essentially analytically with a little bit of numerical thing. And it took a long time to set up this thing. So, it took about 9 years. So today I'm going to talk about results which came out after, 20 preliminary papers. The final results which have come out in the last 2 years give us resistivity and DC using this technique, which has been kind of developed over 9 to 10 years. And the method does not use expansions in large N, large S, or large anything. See, the typical rules of theoreticians is to embed your problem. You got electrons spin half, and it's two component electrons. They say, let's start with N equal to N very large. Let's impose some symmetric group, whatever, symplectic or what have you, all kinds of symmetries, and do a Large-N expansion and then pray to God that the Large-N expansion converges. It's a way of doing physics which has led to no solid results in this area. I mean, other places where Large-N has worked, not here. It hasn't given us any predictions that we can check. Basically, I mean, to put it very bluntly, it's been a waste of time to do a lot of these slave fermion theories, slave boson theories. People have used a lot of these things. They're very problematic, and the problems we discovered, there are some theorems which they violate, called shift identities. I'm happy to talk about them with anyone who's interested, who's very fond of slave bosons, slave fermions. You'll be very angry when I say that, but I'm happy to talk to you about this. So we don't use any auxiliary degrees of freedom. We don't use perturbation theory in interaction. And we don't use large-scale numerics. So basically, the whole thing can be done analytically. And I want to just give you a flavor of what we can do and what we found. So the nature of the solution found by this iterative solution process is a Fermi liquid at very low temperatures. And the Fermi temperature turns out to be very low, 50 degrees Kelvin, 70 degrees Kelvin. And the reason you don't see them in experiments is because it's buried inside the superconductor. Superconductivity is happening at 100 degrees, 50 degrees. So, but if you can kill the superconductivity and go inside, you will find this Fermi liquid behavior. And the quasiparticles are very fragile. And I will define this quasiparticle weight. It's like the wave function renormalization in QED, something very similar. But Z in this problem is very, very small. And that is linked to the fact the Fermi temperature is very low. And superconductivity is also very fragile. It's strongly D wave. You only get D wave superconductivity, which is very good. That's what the experiments find. But it needs some help from band parameters and so on. And TC is roughly 100 degrees Kelvin. And just to give you a flavor of what we are finding, this theory can also be applied to the limit of very large dimensions. And for very large dimensions, there are exact solutions known now, thanks to something called the numerical renormalization group, NRG, or DFT and NRG. Ken Wilson sort of pioneered that. DMFT came from the work of Antoine George, Cotillard, and so on. So that our theory matches that theory beautifully, exact results. So what you find is that you find a very small regime of liquid behavior, like resistivity going like T squared, and then it goes linearly, crosses over to another linear regime, and then crosses over to yet another linear regime. So, this is like, there are 3 linear regimes and 1 quadratic regime. So this is like very complex behavior, which comes out of the theory. And this kind of is a picture which should be kept in mind. In particular, I think a lot of the recent work by some very optimistic people finds linear resistivity, and they claim to have solved the problem. But actually, in reality, there are different types of linear temperature regimes with different intercepts. If you extend this, the intercept at T equal to zero resistivity can be either positive, negative, or zero. So there are a lot of complexities in these things which are they're there, and our calculations find them. And I'm going to show some resistivity curves from the calculation and some equations for some results for the TC. I'm actually not very optimistic about time. I have okay, so I should at least tell you what the Hamiltonian is. Rahul, you want to say something about the time?
Rahul? No, you can go ahead. We have no fixed time as such. You can take maybe another. I'll try to
condense things in about. I have 10 minutes anyway, so I'll try to finish.
You can say you have 15 because we started a little late as usual, but you can go on beyond.
Okay, I'll take 15 minutes, and after that I'll wind down. Okay. So, okay, at least the Hamiltonian should be written down. So this is like the Tij Hamiltonian, except I've got these hats here. So what are these hats? These hats are basically projection operators sandwiching canonical electrons. So basically this C hat is like the regular C operator, but sandwiched by a projection operator, which destroys double occupancy. So, if you think of the Hubbard model, you would not have this hat. You would have a T hopping. This is nearest neighbor, this is second neighbor hopping. And you would have a U times N up and down. And the limit when U is very, very big, you would have single occupancy. And you can basically do Brillouin-Wigner theory with that large U, and it will give you effective Hamiltonian. So this is the effective Hamiltonian of the Brillouin-Wigner theory, in which these operators come with sandwiches of projection operators. So you have thrown out a big fraction of the Hilbert space. And because you've thrown out big portion of the Hilbert space, the anti-commutation relations of the electrons are no longer canonical. You get a Lie algebra. So the C hats satisfy a sort of a graded Lie algebra, if you wish. Unlike CC dagger is delta function, you get this extra thing. So they're very much like angular momentum commutation results. You take S plus S minus, you get SZ. It's something like that with fermionic flavor to these electrons, okay? And Schwinger-Tominaga methodology is very, very beautiful. It works. It doesn't care about whether you have canonical or non-canonical operators. And it's very familiar to, in fact, many people how this Schwinger-Tominaga method works. You take the Hamiltonian and add some external potentials, okay? External potential, nu, couples to the density. And this can be generalized to have spin variables, spin degrees of freedom. And using this external potential, you can generate exact differential equations for functional differential equations for the electron propagators. Okay. Oh, what is the size of the hardcore? Dr. Govindrajan, did you ask me a long time ago?
Yeah.
Size of the hardcore?
Okay, I just try to guess. Now I have a new question. Since you have changed the commutation relation or anti-commutation relation,
Yeah.
would you say that the fermion no longer behaves like a fermion?
Yeah, I mean, they are no longer canonical electrons. But they're certainly anti-commute at different positions. So some of the fermionic flavor is preserved.
Okay.
But they are
They're also not anti-commuting, no?
They're not simply anti-commuting. At different sites they are. If I is not equal to J, they're anti-commute.
Okay. So,
but if I equal to J, then you have the extra piece.
So it is no longer hardcore fermion.
Or these are hardcore with a vengeance. The hardcore, and they have other restrictions, which
That's why
they're definitely hard.
Yeah. So the size of the hardcore extends.
So here the size of the hardcore of these electrons is single site. So on each site you can put only one electron with either spin up or spin down. But if you try to put an up and up is of course prohibited by Pauli principle. But if you put an up and a down, normally it's okay. Normally there's no prohibition to putting an up and a down on the same atom. But here, this projection operator throws out those configurations. So that is the reason why, that's why these are non-canonical. Okay?
Thank you.
Right. So, so that's basically the story. You have a exact functional differential equation in which you can find an iterative solution of this by putting a parameter lambda which lives between 0 and 1. So basically, the n plus 1th G can be found from the Gn by a systematic expansion in lambda. So this is, ultra condensed form of about 15 papers. So I'm I really apologize to you because I have not been able to give you more details of this, but it'll just take a lot of time. But I want to emphasize the idea behind that is so simple. The idea is that if you have an exact functional differential equation, you should be able to iterate it. And if you iterate from the non-interacting value of the Green's functions, then there's a chance that you will preserve some continuity, adiabatic continuity or isothermal continuity, perhaps, So that's what happens here. So I'm demonstrating that this works, demonstrating that the continuity works is a long story, which I will spare you. And actually solve it, and even at very low order, like second order, we already get excellent increment. So we've by now done up to third order, and but second order already does really well. So I want to just say one word about Z of K, this quasi-particle weight. See, this is like the wave function renormalization in field theory, but in condensed matter, what this means is if I take the interacting ground state, and if I destroy a bare particle at time t equal to 0, and after a long time t, try to create back the same non-interacting particle thing, and take the overlap with this, this is the Z. The square root of this is the Z. And if Z is 1, this means that, of course, this are exact eigenstates of the destruction operator. But and if Z is 0, this means that the interacting and the non-interacting states are orthogonal to each other. But what we find here is that Z is very small, it's like on order 0.1, 0.08. And this comes from a real calculation. So we can actually calculate the Green's functions and compute these Z's, and they turn out to be really small. And that's a critical factor because that determines the Fermi liquid temperature. So I'm going to skip one slide. I'm going to just run to the experimental data. So here are the 3 single layer experimental data. Yeah, Ganesh, yes.
So what is the input, though? The density of holes, is that an input? Does that enter in the G naught that you start with?
No, so G naught satisfies, G naught has got chemical potential,
Yes.
And the chemical potential is determined by requiring a sum rule. Okay. So I mean, just like ordinary Green's functions, you want to find the number of electrons.
Yes.
You take the trace of G.
Yes.
And that gives you N. That's exactly what we're doing. So our Green's function contains a Lagrange multiplier, which is a chemical potential, which is determined by the number sum rule.
I see. Okay. And that is so in principle you can tune the doping.
It change and continuously from 0 to 1.
I see.
Yeah. Okay. So in fact, that is the only parameter we have, because we've a temperature. We've got the temperature. So temperature and the density are the only 2 parameters that we have. And we can calculate the Green's functions. And from the Green's functions, we can compute using Kubo formulae, the resistivities, and so many other things.
Yes.
So the whole machinery of standard many-body physics can be imported into this thing because you're getting a very interesting G, which encodes, all these very strong correlations. Okay, so that's what is done here. So you've got 3 of these prototype single-layer systems. One is this lanthanum copper, strontium copper oxide. Other is bismuth strontium, BISCO, they call it. And each of these is interesting because they're not like a single density. Each of them has got 8 or 9 densities, There are lots of densities here. And both of these look similar. And the electron-doped system, which is a different type of a high TC superconductor, where resistance actually goes like T squared. So this is not, this got only one puzzle. Why is TC so high? But the transport looks exactly like a Fermi liquid. And the difference between this and this happens to be one of the band parameters, And maybe I should have shown you that. The band parameter, T prime over T, is the ratio of the second neighbor hop to the first neighbor hop. And it can change sign. And the change in sign of T prime from negative to positive, that's what is supposed to be responsible for the difference between this guy and this guy. And our calculation supports this fully. So what I'm going to do next is I'm going to calculate from the theory the resistivity for corresponding to these parameters. And it's almost a zero parameter theory because there's essentially only one parameter which goes into the theory, which is taken from experiment. So T prime over T is found from photoemission, and the lattice constant CL is taken from crystallography. And T is only one parameter that I have to assume. So I parameterize these 1, 2, and 3, skip this third row. Okay, that's also works, but it's very sparse data. So I'm not very keen to talk about this. The first, second, and the fourth guy, they have parameters which are all taken from experiment. And the resistivity in this theory is a product of the von Klitzing resistivity, which is H over E squared in terms of fundamental constants. And then we have a rho bar, which is a scaled resistivity, which is a function of these dimensionless numbers, T prime over T, J over T, KBT over T, and delta. Delta is the filling. Okay. And so for these three systems, I want to first show you the theoretical resistivity and then I want to compare with the experiments. So I basically did the resistivity at the same densities at which the experiments were done. So you see these have a small quadratic regime followed by a linear regime which bends over somehow. Okay. In each of these densities, you could say the same thing. It has ultimately, asymptotically, at the lowest temperatures, it's got a quadratic regime. Then it goes linear, and then it kind of curves a little bit in the opposite direction. It's concave downwards. It goes like minus x squared here. And for these three systems, these parameters are taken from experiment. And you see LCCO is going beautifully like Fermi liquid, like a T squared. So how do these compare with experiment? Let's check that. So here, this is LSCO. And the resistance is in milliohm centimeter, temperatures in degrees Kelvin. So all these are done on absolute scale measurements. And here there is a pair of numbers. One is the density. 0.12 is delta of 0.12. Here is 0.2. And here it's 0.21. And the second guy is basically the intercept. I mean, these have some impurity resistance, which has to be estimated. I mean, the experiments have impurities which you have to ultimately account for. And we do like a reasonable estimate of the impurity resistivity. And then you see, I mean, theory is blue, experiment is red. So over these temperature regimes at which people have measured things, it's sort of remarkable that the theory and the experiment are very close to each other. So we have, I think, a good estimate of...
There's a question from Deepshika.
From? Yes.
Dr. Deepshika, you can unmute and ask.
Yeah. Deepshika, go ahead.
Yeah. Hello, Professor Shastry. This is Deepshika here. I wanted to ask if the crossover from T squared to T, does it represent some kind of a phase boundary in the phase diagram?
Yeah. So okay. So this is a very good question. I mean, I would say that the transport crossovers are not
because they are above TC, right? I mean, it must be above the superconducting dome then. Yeah. In that part of the phase diagram.
This is the normal state. Yes, this is the normal state. Yes.
Correct. Yeah.
So they're not really related to any phase transitions or crossovers in the sense of phase transitions, but they are just crossovers happen in transport, which is why I showed you that resistivity having three linear temperature regimes, in the infinite dimensional solution. I don't know if you remember that, but I showed you here this.
Right. So I was wondering if these changes from one kind of if T square Fermi liquid kind to a linear behavior would represent
It's not selective phase transition. Now there's some entropy release, and that can be estimated. We can calculate those things, but there's nothing critical there.
I see. Okay, fine. Thank you very much.
Sure. And this is the other system, yes, LCO, where again, the story is the same with 7 densities. Again, the theory and the experiment match almost perfectly. I mean, but you may say that, look, Sriram, you are assuming impurity resistance, which is ultimately maybe you're fiddling something. So then we talk about NCCO. Here, there is no impurity contribution. Or put it this way, the experimentalists themselves removed the impurity contribution, which is very easy to do because here the curves are quadratic. So if it's quadratic, you can get rid of the impurity contribution very easily. So here, without any impurities, there's a matching between theory and experiment. So I would claim that we have a fairly strong understanding of the resistivity of the one-layer system, and this is as a function of density, as a function of temperature. And to me, this is significant, but I'll leave it to you. I mean, please feel free to be more skeptical than I am. And it's good to be skeptical. But I think things are going better than I had hoped for. Rahul, can I take 3 minutes more? It's 10
yes, please go ahead. Yes.
Okay. So how about superconductivity? So this is a very new paper of ours, mine, on the superconductivity. And the problem has been around for a long time. In fact, many of you know that Anderson, Bhaskaran, and Zhou wrote a very influential paper in 1987. And so you may say, why are we still talking about this? Well, the reason is nobody, in the last 30 years, people have completely forgotten this paper. And the reason is, of course, although they are very, very clever in talking about superconductivity, they had no idea of how to handle the strong correlation aspect of this. So strong correlation theory did not exist in the year 1987. And they were forced to make some very violent approximations, and people jumped on them. And, so basically, if you look at the community today, there is very little faith in the old papers. But here, what I'm going to show you is that the one idea which survives from this old paper is that J in the TJ model is the glue, is what is creating the Cooper pairs. And the strong correlations require a lot of nursing. You can handle them with care. And at the end, you get something which is sort of interesting. I would jump to the results and show you that TC as a function of delta has a behavior like this in the theory. And this peak is a little exaggerated. I think a few hundred Kelvin is more reasonable. That's probably what I have. Let me finish this, Ganesh, and I'll come to you in a minute. So basically what I have is from this theory, extremely correlated Fermi liquid theory, I compute the equations for superconductivity a la Gorkov. Gorkov's theory, was for BCS, but it was backed up by Eliashberg. So Eliashberg came about 10 years afterwards, and he gave a very, very important paper explaining how the renormalized Green's functions change Gorkov's equations. And within the electron problem, there's something called the Migdal theorem, which says that the vertex corrections can be neglected. And in that situation, the Eliashberg equation becomes exact. Now for cuprates, there is no electron phonon problem, and there is no Migdal theorem. So you have to find some other ways of earning a living. And so what I have done here is found a way of finding something like an Eliashberg equation. And it's a very tedious and a very long paper, and I can't summarize it in even 1 hour, actually. But let me just say that the answers can be written down finally in a form which looks very much like VCS. So you get an effective coupling constant G effective, which contains the quasiparticle renormalization Z. So if Z goes to 0, G effective goes to 0. So this is what is killing superconductivity. If you have very little quasi-particle weight, there is nobody willing to pair up. The Cooper pair is a pairing between quasi-particles. But if the quasi-particles are dying due to interactions, you can't form a condensate. So there is a battle between the tendency of J, which wants to pair things, and the role of quasi-particles, which are disappearing. So that balance is a very delicate balance and can be captured in a very long calculation. And I would say that this result basically gives some hope. And actually, for the first time that anyone has found a dome-like structure with two densities, like one density here, which is non-zero, and one density here, and a peak density. So delta smaller, delta greater, and delta star come about because the G effective becomes non-trivial and then goes down. And this peak is related to a peak in the density of states. So, I think this kind of this effect, coupling constant as a function of delta has peaks which are reflected in the TC thing. So I would say it's been very challenging to compress the story into 5 minutes. But you'll forgive me for making a mess of it. But the paper is available, and if you're interested, do look at that. And I'm happy to talk to people further. Yeah. Hassan, somebody questions? Hassan? No. Okay, so I would say I'm duty bound to show you the names of my collaborators, lots of students and postdocs and some collaborators outside. And finally, I want to show you one cartoon, which is it's a whodunit story with high TC, who did the crime. And usually it's a global warming, but I think we've narrowed it down to TJ model and strong correlations. I've tried to convince you that these are responsible for, at least for the cuprates. So I'm going to stop at this and take any final questions. Thank you.
Okay, thank you, Sriram. We are a bit over time, but it's all flexible. So feel free to ask any further questions. You can just unmute and ask. Mukul, go ahead.
Yeah. So first, thank you for this very nice talk, sir. I had 2 questions. Actually, the first one was, it's remarkable how actually we're starting from a TJ model limit with no double occupancies, which effectively corresponds to a U going to infinity limit of the original Hubbard model. One is actually able to get to a regime where the low temperature metallic state is a kind of analytic continuation of a Fermi liquid, of a free Fermi gas in the sense of a non-zero quasi-particle residue. The point was, what I wanted to ask was basically, if one goes by the argument which was made by Anderson in a related context, what he was saying was that if you dope carriers in a Mott-Hubbard insulator, then for small doping, the absence of recoil during a scattering process for large U will basically kill the quasi-particle altogether, giving you a metal which has no poles but only a branch cut. Now, this seems to be the state at high temperatures where the green function essentially has no Z. But at low temperature, it seems that Z emerges out of this incoherent soup, notwithstanding strong scattering. So, how does this magic occur in the Dyson Schwinger machinery that you described?
Okay, that's a very beautiful question, very sophisticated question, and I will answer by saying that I actually think Anderson is wrong to say that recoil as the recoil argument which Anderson gave was clearly wrong, because basically, even the X-ray infrared problem, if the impurity has a finite mass rather than infinite mass, then the orthogonality catastrophe is cut off. There's a famous work of T.V. Ramakrishnan in Toulouse and so on, which shows that. So actually, technically Anderson's infrared catastrophe argument about why the quasi-particle weight should be 0 is wrong. So actually, there's a philosophical difference between what I am doing and what Anderson said and what Bhaskaran and even Chandra Verma. So many people have said it's a non-Fermi liquid. I'm saying no, it's a Fermi liquid. I'm saying it's a Fermi liquid with a very low Fermi energy. And your second part of your question was, how does this emerge from Dyson-Schwinger equations? And the answer to that is, actually, there is a new proof of the Luttinger-Ward theorem. I actually gave a proof 2 years ago. And the key element there is like a thermal, like adiabatic or isothermal continuity. Continuity is what matters. And second thing is, if you don't have phase separation, then the range of volume is preserved. So I think both conditions are satisfied in the ITC system. So Luttinger volume theorem works. Now, is Z really 0 or non-zero? That theorem doesn't necessarily answer that. So I cannot say that experimentally people know for sure that Z is non-zero, but in small number. But then that's actually a very challenging and important problem. I think in the next couple of years, if people can devise sharper tools for discovering, actually this turnover, actually what I'm saying is that there's always a turnover to Fermi liquid quadratic behavior at very low temperatures. And it should be visible in so many experiments. And if you see them in some experiments, then that's equivalent to saying that there is a low Fermi temperature. So I think it should be seen. I predict that it will be seen. And I hope somebody will take up this challenge and see if it happens or not. And like in all of physics, there is a probability that what I'm saying is wrong, that maybe things don't turn around. And in that case, it is a non-Fermi liquid. And, fine, you can throw out all these my theory completely. On the other hand, at present, there is no other theory which is quantitatively anywhere in this level of description that we have. And it doesn't mean it's right. It just means so far it is not wrong. So we are waiting. We're waiting to see what happens.
Thank you, sir. So I had actually one small question as a follow-up of this. Which is basically, in many experiments for hole-doped cuprates, superconductivity occurs right from a metal which has a linear in T resistivity without the system having entered into a regime where there may be a T squared component. So, where TC is of order 100 Kelvin, one does not see any T squared component in the resistivity. The TC drops from a metal which has a linear in T resistivity. This would formally correspond to a metallic state which is incoherent, and by implication a state where effectively Z has had no chance to become finite. So in that case, what is the nature of the quasi-particles? I saw that you mentioned it during your talk already. But what is the nature of the quasi-particles that pair up to give Cooper pairs?
Actually, that is the key point. I think ultimately superconductivity, happens with quasi-particles which are very ordinary quasi-particles. It's just that the weight is very low. But it's not like a Bose condensation or something like that. It's like regular. In fact, inside the superconducting phase, that the physics looks very much like BCS. Apart from some, thermodynamic ratios and stuff like that apart.
Yeah.
In general, it looks very much like a good regular superconductor.
Yes.
So quasi-particles they have a small weight, but other than that, they are just like quasi-particles, and they're coherent. And they. Okay, Mukul, I need to move to other.
Yeah.
There are
Other questions. Sorry. Thank you, sir. Thank you.
Yes. So Ajit has his hand up. Let me also just check with Sriram. It is 10:15 p.m. at your time. So are you good to
I'm
go?
perfectly fine. I'm happy.
Okay.
I'm happy to.
Right. Okay. Ajit, go ahead.
Hi, Sriram. Thanks for this very nice talk. I mean, one experimental question I had was like, have people tried to measure the Hall to show that the Luttinger-Wald theorem holds to a very good approximation? And the second was a theoretical question based on how robust are these features in the sense that, let's say, if I fiddle around with the TJ model, add some next nearest neighbor hopping or something like that, then how robust do these features be?
How robust are what features?
Like these theoretical results that you showed of about how far the TC is, or let's say these even like these quasi-linear linear resistivity of temperature as a function of temperature. So let's say is that like crucially dependent on using the TJ model, or let's say if I move away from the TJ model, then
I think a lot of this resistivity kind of stuff is coming from the Kurzweiler projection. J is not so important. So if you have some other favorite model, but you also have this constraint, constrained Hilbert space, you would get the same.
So this double occupancy is the more crucial feature in that sense.
Yeah. Actually, this strong correlation aspect, which is the strong U aspect, that is what is creating these weak, fragile quasi-particles. And the fragile quasi-particles self-consistently create a very low Fermi temperature, But all these, I would say even that is sort of a fairy tale, because ultimately, if somebody presses me to the wall and says, can you explain to me why then did you find these 3 T-linear regimes in the plot that I showed you, I would say, look, it's still a little bit of a result which is coming from a strong calculation. And we are reading the tea leaves. We're trying to give a qualitative understanding of a result. I mean, we can ultimately only vouch for the ideas behind the calculation, But calculation has a mouth of its own. It has a voice of its own. It has almost a mind of its own, It tells you what it's finding, So ultimately, this is a problem of strong correlation. There is no, single, simple way of understanding why a lot of these things are happening. I mean, if you do renormalization group, that's something very similar happens there too, I mean, you do things and flows happen in certain directions. Okay.
What about have people measured the Hall to see that the Luttinger-Wald theorem holds?
Yeah, Luttinger theorem holds in the overdoped and optimally doped cases very well. I think in the underdoped materials, you lose some Fermi surface volume, and that's a mystery of the so-called pseudo gap phase. And I didn't even talk about that today because there is a lot of detail and complication there, which has to do with the fact that when you're very close to this jam-packed Mott-Hubbard limit, there are many competing instabilities. So I think there's some other broken symmetry which can swallow up parts of the Fermi surface and charge density formation and stuff like that. So I think the Luttinger volume theorem experimentally sort of violated in the pseudo gap regime, and I'm not even interested in explaining that because I know why it is happening. But there's a broad reason why it must happen. There are a lot of competing instabilities. Usually, the kinetic energy of the electrons is the dominant energy, and it kills all instabilities. But here, when your kinetic energy itself is feeble, nothing is moving. then, I mean, it's like in a bad democracy, every voice has got a megaphone to it, It's something like that. Whereas if you have a very strong stream of reason and logic, and the Fermi energy is dominating things, then instability is, well behaved. I mean, the finite in number, and they come with very strong reasons. So here it's sort of chaotic democracy is a way to understand the pseudo-gap regime. But let's move on to other questions.
Okay,
Adil, you have a question?
Yeah, Adil, you can unmute and ask.
Yes, sir. Yeah. Hello, Professor Shastry. It was a really good talk. Okay. So I had one question. I had two-part question follow-up. So in this 20-second slide, you have talked about the different disorders, not like disorders being so could you go to the second 20-second slide just about this?
Oh,
20
like
second 20 second.
Oh,
20
20 second.
second.
Wow, okay. Right.
Yeah. So you are saying that the disorders easily removed. So these are the experimentally they have removed the disorders. And what type of disorders have they moved? Is it the on-site or the vacancy or the hopping parameter disorders? They have removed.
We don't know. I mean, there is a when you plot the resistivity as a function of temperature, it has an intercept at t equal to 0, which is some finite number. And that comes about from elastic scattering. Elastic scattering can be due to any kind of impurity. We don't know actually what the nature of the impurity is. But what I'm trying to say is that a constant plus t squared, if that's the behavior of the function, the constant is easy to estimate. And the experimentalists did that.
Okay.
Whereas if you have a constant plus linear in t, then it's a bit harder actually for various reasons. I mean, it's surprisingly hard to estimate the constant so unambiguously.
Okay.
So
yes. And okay. I have a second question, sir, regarding this only. Yeah. So has there been an analytical study on the disorders and correlation between different types of disorders? Because in real life systems, we will really find a pure system. So has there been a study on that?
I mean,
analytical or numerical?
Yeah, I think there should be some numerical studies, which I don't know offhand, but it's intellectually not a particularly challenging problem. I mean, I don't think it's very different from say the resistivity of copper due to impurities. It's a similar type of a problem. So I don't think there is anything ultra special. I mean, this issue that we are talking about today, like the nature of the inelastic scattering, this is much more non-trivial. So I mean, I don't want to run down the problem. I think the problem exists; it's a real problem, but I think there are plenty of ways of solving it, and I'm sure somebody has done it. I can't remember offhand. So I have. Sorry, probably not given you a very satisfactory answer, but I don't know actually. I don't know any good reference to that.
Okay, sir. Thank you, sir. Thanks a lot.
Okay.
Okay. Are there any further questions?
May I ask Rajaji?
If you can unmute or if you can type in the chat box if you're not able to unmute.
Okay.
Go ahead.
Yes.
I have unmuted.
Yes, we can hear you. Thank you.
Rajaji?
Yeah.
You can hear me? Yeah.
Yeah. Can you hear me?
Yes, we can hear you.
I can hear you. Please go ahead. Yes. Yeah.
Yeah, it was a very good talk, Sriram. Although I am completely out of touch with these matters nowadays, so I could not grasp the full significance of many of the things which you said, but I could see that it was a very wide-ranging talk, and you have done a beautiful job in understanding these things and talking about it. Thank you very much.
Thank you, sir. Thank you. Thank you so much. I mean, I remember that you were also always very concerned about, theory having to make sense with experiment. I remember in the old days in TIFR, I think you always kind of emphasized taking experiments versus theory comparison seriously, and that's really what we,
Yeah, definitely. I mean, theory exists only if it agrees with experiment. Otherwise, the theory is discarded. Experiment is never
yes.
Experiment is a truth, and
Yes.
you have to explain it. And
Yeah.
condensed matter things are very, very complicated. In my opinion, it is much more complicated in elementary particle physics, which I am familiar with. But nevertheless, people like you, Anderson, Bhaskaran, etc., have done a very, very, very good job in trying to bring theoretical understanding of ITC superconductivity and other things to such a level. I mean, really, it is mind-boggling the kind of theoretical work which you people have been doing.
Thank you very much. And I must, thank my teachers for having, given us a very good foundation. I mean, I remember all these early years in quantum mechanics training in TIFR. Also, Marquez Saab, emphasized so much of experiments on nuclear physics. I can never forget, how serious he was in understanding nuclear matter. And Chanchal also was very serious about data and so on. So I think all my teachers were really.
You were a PhD student, right?
Chanchal, I was Chanchal's. Chanchal, and I also worked one paper with Jha, but I worked mostly with Chanchal. Which, of course, Chanchal went away, very quickly after I joined to Calcutta. So I was left working on my own for a couple of years. But still, Chanchal was, also Varke Saab helped a lot. Jha helped a lot. It was a really wonderful time, wonderful time. Yeah. Okay.
Okay. Maybe we can declare the meeting over now, but if you want to chat some more with friends here, feel free to continue. So let me just end by thanking Sriram again for a very interesting talk. I am not really in this field for the last 20 years, and even if I was, I don't think I'd have understood everything in 1 hour, but it's very interesting that the theory of the cuprates might involve there being a Fermi liquid and not a non-Fermi liquid, as people have been saying since my PhD days. So I hope there are many more developments in this area now. So let's thank Sriram again. Thanks everyone for attending. And I've been recording this, so hopefully it will be up on YouTube at some point.
Thank you everybody, and for me it was such a delight to find Rajaji here. And I wish Bhaskaran were here. Unfortunately, he's having a cataract surgery today. He said, so he's not here today.
Okay, there's somebody in the chat window who just says thank you very much.